We're going to change gears a little bit here and look at modeling translational mechanical systems. And one important thing to keep in mind is that the resulting transfer functions from analyzing these mechanical systems should ultimately be mathematically indistinguishable from transfer functions that we get from circuits. And so that's a really cool thing about control systems, is that we could be analyzing the same type of equation and it could be coming from some chemical process, some mechanical process, some electrical process, but the underlying analysis that we're going to do in this class is all the same for all of these different types of problems. So for our translational mechanical systems, though, we're going to be concerned primarily with three quantities: our force, our velocities, and our displacement. And so we could draw analogies to these for some of our electrical values, our voltage, our current, and our charge respectively. But once we get into defining impedance for our mechanical systems, our analogies don't quite fit one-to-one. So don't worry about that too much if it's confusing. So we also have a handy table in the book, table 2.4. And in the 8th edition of the textbook, that can be found on page 54. And so what this has is a lot of equations which relate our three quantities here, force, velocity, displacements, for several of our common elements. And so if you're like a double E like me, who's not dealt with these in a long time, that could be a good refresher. For some of you MEs, this might be a little fresher in your mind though. So what are these key elements that we're going to look at? Well, we're going to look at three passive mechanical elements. So the first one is our spring. So let me put sort of a little wall or a fixed place here, and we can connect a spring to this. And so for our spring, sort of our key value that we're going to be dealing with our spring is our capital K, or our spring constant. And so in some ways we can say that our spring is analogous to our capacitor in electrical systems. Now the second basic passive mechanical component we're going to look at is a viscous damper. And so with a viscous damper, we can say that this is sort of analogous to a resistor in our electrical networks. So this is a viscous damper, and we'll also use sort of the same idea here to represent frictional forces. So we have, for our viscous damper, our key sort of parameter is F sub V, which is our coefficient of viscous friction. And then our third and final sort of simple passive mechanical element we're going to consider is just a mass. And so we're going to represent that with some mass m, and this is going to be analogous to our inductor in our electrical systems. So as you remember, when we were dealing with our electrical networks, our first step is to apply our fundamental laws. So first step is apply fundamental laws, and from that we can get, if we're in the time domain, our differential equation. So fundamental physical laws. So when we were dealing with our electrical networks, we used Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. But of course, for our mechanical systems, a fundamental law that is often going to be applicable are Newton's laws. And so what we're going to do is we're going to see an example in the next video, and we're going to see how we can apply Newton's laws to get an equation representing a transfer function for a translational mechanical system.